Hi, in this chapter we're going to talk about position tolerance fundamentals. Okay, should be following along with your objective sheets. First objective is to complete a feature control frame for the position tolerance, properly using the diameter symbol, the material condition modifiers, and datum references. Number 2, sketch the proper location and shape for a position tolerance zone. Number 3, describe the effect of an MMC, LMC, or RFS modifier on a position tolerance. And number 4, provide examples that prove the validity of the MMC concept as it applies to position tolerances. And finally, we had some terms for you to know the definitions of. Okay, what are position tolerances? Position tolerances are specified to get the required location accuracy of features of size and bounded features. These may be used on multiple or single features, and the tolerance zone shape is determined by the functional requirements for the feature, and material condition modifiers are applicable for position tolerances, and we're going to discuss those in detail. Here is a feature control frame. A feature control frame is placed adjacent to the hole size specification. So in this case right here, we have our hole size specification right here, and then we have our feature control frame. This is the symbol for positional tolerance. It looks like a bullseye or a target. The diametrical tolerance zone shape is required for holes. Okay, so that's this right here. We have a diametrical shape for the tolerance zone. Basic dimensions define the perfect locations of the holes. So in reference to some datums here, okay, for instance C, this is datum C, we have this 450 and we also have this 825. So these are defining our perfect or true positions of the holes. That's all done with a basic dimension. Feature control frame defines the allowable location deviation. Okay, so this hole is allowed to vary by 5 thousandths in a diametrical zone. And for this example, the location tolerance applies at MMC. That's our MMC modifier right here. So let's talk about some more feature control frames. We can have a inch feature control frame or a metric. We can have 2 single elements, 2 single segments, 2 feature control frames, or we can have a composite feature control frame. We're going to talk about what that means. Let's talk about the material condition modifier. Okay. In Rule 2 of GDT, we said the RFS modifier is assumed unless the MMC or LMC modifiers are shown. So in this case, we have a MMC modifier shown, so therefore the MMC modifier is in effect. Over here, we have a MMB boundary to datum B. Is applicable in reference to datum feature of size or a bounded feature. So in this case, we have a RMB, an MMB, maximum material boundary modifier on datum B. Okay, position tolerance zone. Okay, so the zone has a defined shape, size, location, and orientation. Basic dimensions and references to datums define the location and the orientation. And if it's an axis or a surface interpretation, these two different methods give differing results. So let's talk about the positional tolerance zone. Okay, so in this particular case, we have a prismatic part. Datum A is the flat surface, datum B is this other flat surface, and datum C is the smaller flat surface that sets up our datum reference frame. And then we have these 2 holes, plus 7 thousandths minus nothing, with a 24 thousandths MMC true position. What does that mean? Okay, so that means I have a 24 thousandths diameter tolerance zone centered about the true location. The true location is defined by these dimensions here, these basic dimensions, and then we have a 24 thousandth zone around all of that. And the tolerance zone is going to be perpendicular to datum A. So that is essentially what that tolerance zone means. Now, basic dimensions. Basic dimensions must be used to define location when position tolerances are applied to features. These basic dimensions, they define the true or perfect position of your holes or features. And these basic dimensions are related back to the datum feature reference frame. In this example, you can see we have a datum B here, and then we have the 825 dimension from datum B locating the holes. Okay, and then we also have datum C over here. We have the 900 thousandths dimension and 1.575 dimension, again locating the position of those holes relative to the datum surface. Okay, so what does this mean? We have tolerance zones centered on the true position. The holes here are not shown in this case, and then those are our 24 thousandths tolerance zones. Okay, relationship to datum reference frame. Location measurements made relative to the datum reference frames, that's a perfect coordinate system. Measurements not made relative to datum feature surfaces will have variations and cause measurement errors. Okay, so what we try to do with GD&T is we try to use datum simulators to pick up the datums so we can measure our parts faithfully. Okay, without picking up the datums and you're just going to try to measure the holes, you're going to be inaccurate. I mean, the location of the holes, you're going to be inaccurate. So the basic dimensions always define the perfect location relative to datum features referenced in the feature control frame. Okay, so here we have our datum features, B and C. We have basic dimensions locating the holes from those B's and C's. And then when we go to inspect the parts like we're showing here, what we're going to do is we're going to have datum simulators that pick up datum A and datum B, and they're going to find for us the location of these datums so we can get an accurate position, a measurement of the position tolerance. Okay, let's talk about the effects of RFS versus the effects of MMC. Okay, so based on Rule 2, no modifier is required. RFS will always be assumed. That's Rule 2 of GD&T. The size of the produced hole has no effect on the positional tolerance. RFS is always used when holes have a zero clearance or if a hole is used for a press fit or etc., etc. What we're looking for is, parts in their proper location for RFS. So what we have here is we have an example. This is a hole tolerance. RFS is assumed. Here is the hole size. What happens here is that if our part is produced at the MMC, we have a 25 thousandths allowable position tolerance. However, if our part is made at 510 thousandths, which is our least material condition, we still have a 25 thousandths allowable position tolerance. Okay, so the tolerance does not change with the manufactured size of the hole. That is the effect of RFS. And it becomes a little bit more tricky to check versus our MMC condition. Okay, based on that, we're going to talk about the effect of the MMC. The MMC modifier is applied to the feature control frame after the tolerance value. The MMC modifier indicates that the tolerance applies when the hole is at its maximum material condition. That's the smallest hole. As the size of the produced hole is above MMC, more positional tolerance is allowed. This is typically used for clearance hole applications. If the hole is larger than MMC, it can be off the true location by more and still fit in the assembly. Okay, so you get bonus tolerance as the hole deviates from the maximum material condition. I'm going to stop this video right here and pick this topic up on the next one.